Hello everyone. Today in this video I will be working through my implementation of transformer model from scratch using only NumPy. And I implement the decoder only transformer by building an GPT-2. So let's dive into my code and explore how each component functions. So to begin with, my transformer model follows the GPT architecture, which consists of several key components like the layer norm, the feed-forward functions, and the multi-head self-attentions. So using these components, I will build the GPT block and finally the GPT models. So let's explain each of these modules before demonstrating how they come together into the full GPT model. So the layer normalization helps stabilize the training by normalizing activation across the feature dimension. So in my implementation, I initialize two parameters, the gamma and the beta, which scale and shift the normalized values. And in the forward method, I compute the mean and variance, then normalize the input and applies the gamma and beta. So the next part is the feed-forward function, and this consists of two linear layers and a ReLU activation in the between. So the first in linear layers, I use the tensor dot to compute the input to project it into higher dimension space. And then is a ReLU activation to add some nonlinearity, and then is a second linear layers projects the activates back to the original dimension. And the next part is multi-head self-attention module. It enables the model to capture relationships between tokens in different parts of the sequence. Instead of relying on the single attention mechanism, we split the model dimension into multiple heads. Each of these learns different aspects of the relationship between tokens. And here we define the Q key V refers to query key and value, which metrics are computed from input sequence used the learned with parameters. And the attention scores here is calculated as the scaled dot product of Q and K. And the casual mask is applied to prevent future tokens from being attended to. And the softmax normalizes the scores into attention weights, which are then used to weight and values V. And the output from each attention head is concatenated and project back into the model dimension. And then is the GPT block. Here at the right, I put a image shows the architecture of the GPT block. So we will build the GPT based on this structure. So the first layer is the layer normalization, is to stabilize the activations before passing them to the attention and feed-forward layers. And then is the multi-head self-attention to model the token dependencies. And the third one is on the residual connections here to concatenate the gradients to flow through the network efficiently and helping with the training stability. And then is another layer norm here, and I defined in LA2. And it ensures stability before feeding the result into the feed-forward network. And then is the MLP here, so I define the feed-forward as the MLP. And is to further process the attended representations. So finally, we have another residual connections to concatenate the features after the second layer norm to the output. And here is the implementation of the forward functions. First, we will use the forward to implement the layer norm and the multi-head self-attention. And then we use the addition algorithms to add the residual connections here. And then is apply another layer norm and feed-forward network, and finally another residual connections. And the final part is the full GPT models. As we can see in these images, we conduct some position encodings and token embeddings at first, and then we have several transformer blocks here, and then is a normalization block to stability before output projections. And finally is the output projection layers to map the hidden states back into the vocabulary logics. So in our implementation, we have the several initialize of the dimensions and size, and then we indicate the token embeddings and the position embeddings, and then is the layers. We defined several the transformer layers by use the GPT block we defined before, and then is the layer norm we use to have the final stabilized before the output. So in the former layers, we first look up the token embeddings here, and then we add the position embeddings at the graph shows, and then we pass through each transformation blocks using the forward functions. And after go through the transformer block, we finally apply the layer normalization and the final output by using the linear projections. And here is an example use case. I tested the model using a dummy input and expected the output as a tensor of shape. So here we need to be the batch size, the sequence length, and the vocabulary size. So let's run this script. So here you can see the output is 2, which we defines the batch size here, and then is the sequence length, and finally is the vocabulary size. So that means our model can successfully process the vector and finally output the shape that's same as what we defined. So that is what I implement the transformers.